Alrighty, class. Well, I don't mean to scare you by putting my picture here on this video. But anyways, since I'm not in class today, I figured I'd make this video to go over some of the worksheet problems that you had due for today. I'm sure that you have lots of questions about them. So let's go over a few of them. The first one I wanted to talk about were these here, 23 and 24. And we'll tackle number 23 here. So 23 has a set of parametric equations. And there they are, x equals 5 cosine t, y equals 5 sine t. Florigators. And our job is to eliminate the t variable. So these are my two equations. 5 cosine t, and then I've got y is equal to 5 times sine t. Well, the key to eliminating the t variable here is to remember our trig identities. If I take the square of both sides of these equations, the x becomes x squared equals 25 cosine squared t. If I square the y equation, I get y squared equals 25 sine squared t. And now I can add these two equations together, and I will get on the left side x squared plus y squared. And over here I get 25 cosine squared t plus 25 sine squared t. You probably see where this is going. But over here I can factor out a 25 common factor, and it gives me cosine squared t plus sine squared t. And Rashawn will tell you that cosine squared t plus sine squared t is equal to, what is it, Rashawn? That's right, it's equal to 1. And so we end up with x squared plus y squared is 25. And that equation there, once we've gotten rid of the parametric variable t, is a circle with a radius of 5. And 24 is done much the same way. You might have a question. I'm sure that somebody has a question about number 49. So Orlando hits a ball when it is 4 feet above ground level with an initial velocity of 160 feet per second. The ball leaves the bat at a 20-degree angle with the horizontal and heads toward a 30-foot fence 400 feet from home plate. Now, we are going to, excuse me, we're going to draw a picture like we normally do. And I'll do my best to make this neat. But anyways, so there's the ball. It's going to be hit here, and it is going to travel. And then there's going to be a 30-foot fence out here. The initial velocity vector is that right there, and it is 160 feet per second, and it makes a 20-degree angle with the horizontal. We know the trajectory of this baseball is going to look something like this. We know this distance is 400 feet. I also know the height of this wall here is 30 feet. And the question says, how strong must a split-second wind gust be in feet per second and acts directly with or against the ball in order for the ball to hit within a few inches of the top of the wall? Estimate the answer graphically and then solve algebraically. Basically what we want to do, we want to change the velocity of the ball so that it is going to take a trajectory that would look like this. and hit the top of the wall. Now, the first thing really that we have to do is we have to come up with the equations that we're going to represent the motion as it's given at 160 feet per second at 20 degrees. The parametric equations are x is equal to v0x or v0 x times t, and y equals v0 y. Let's scratch that. A little bit ahead of myself here. That's going to be negative 1/2 g t squared plus initial velocity in the y direction times t plus h0. Now the way that we're going to come up with these initial velocities in the x and y direction is we're going to take the 160 and break it into its two components. So the initial velocity in the x direction is going to be the 160 feet per second times cosine of 20 degrees. Initial velocity in the y direction will be 160, but we'll multiply that times the sine of 20 degrees. I'll bring my handy dandy TI-84 calculator into the picture. So I will take 160 multiplied by the cosine of 20 equals, let's make sure that we are in the right mode here. I am not in the right mode. So we will come down and put ourselves into the degree mode and hit enter. And we will quit out of there. We'll go back up, grab this, execute it again. There we go, 150.4. Let's just round it to 150. So this is going to be 150 feet per second. And then we'll take 160 times sine of 20 degrees. 54.7, we'll round that to 55 just for keep things a little simple here. So that'll be 55. We know the initial height of the ball when it is hit is 4 feet, so that's what the h0 is going to be. We know that g is going to be 32 because this deals with feet. Therefore, here is going to be our two equations. We're going to have x is equal to 150 times t. The y equation is y equals minus 16t squared plus 55t plus 4. And those are the two equations that represent the motion. What we want to do is find out where is the ball going to go with these two equations. Is it going to go over the fence or is it going to hit below the top of the fence? So that's the first thing that we have to try to figure out. So what we'll do, we know that the ball is going to travel 400 feet in the x direction. So I can solve for t using the x equation. And t is going to be equal to x over 150. So that's 400 over 150. .400 divided by 150 is 2.7. So we'll call this 2.7 seconds. What we want to do now is we want to figure out how high the ball is at 2.7 seconds. So we're going to take the 2.7 and put it in for t into this equation here. And we want to see, and remember what we're trying to do here, because I know that at 2.7 seconds the ball will have traveled 400 feet along the x-axis. So we're trying to figure out where along this line right here is the ball at that exact moment. If I put 2.7 in, bring my calculator back over, and grind that out right there, I have 16 times 2.7 squared. I will add to that the 55 times 2.7, and then I'll add to that 4. And we get 269. Well, you could probably say I made a mistake there. Let's go back and grab this. I need to put a minus sign in front of the squared term. So we will do a insert and hit a negative. And there we go. Okay, that's better. 35.86. We'll round that to 36 feet. So what that means then, class, is that when the ball has gone 400 feet, it is 36 feet above the ground. So it is right here, 36 feet, which means it is 6 feet above the top of the wall. So obviously what we're going to have to do is we are going to have to figure out what should the wind speed be at the moment that the ball is hit in order to slow it down so that instead of it being 6 feet above the wall, that it hits the top of the wall. Now, I hope somebody maybe figured this out, and I'm going to give you kind of a clue here as to how we're going to do this. But what we're going to do is we're going to have to figure out when the ball is at 30 feet above the ground, because the ball is going to take this trajectory that I had here. I'll make it a blue trajectory here. I guess that's purple, but it's going to go like this. Now, there is going to be some point in time where the ball is 30 feet above the ground, but it's going to be beyond the wall. And also, you probably know, therefore, that over here, there's also going to be a point on the way up where the ball is 30 feet above the ground. If I go to my equation for the y variable and I put 30 feet in for y, I can solve it for t, and it's going to give me the time. One of the times will be here when the ball is at 30 feet on the way up, and it'll give me the time over here when the ball is 30 feet above the ground on the way down. What we'll do then is we will go ahead and put in, I'll scroll down here, we're going to put 30 in for y, and we get this equation. And our job is to solve for t. And so I'm going to, this obviously is a quadratic, so I'm going to have to subtract 30 on both sides, and I'm going to get minus 16t squared plus 55t minus 26. We have to solve this for t. We're going to have to use the quadratic formula. The other way that you could do it is you could take your TI-84 and you could graph this in regular mode and see where the x-intercepts are. I'm going to show you how to do that because it's pretty instructive for us to know how in the world we can do this. I am going to go here in my calculator and make sure that I am in the function mode right here. You may be already, most of you are probably in parametric mode right here, but move your calculator into the function mode because we're just going to put in an equation that is this quadratic equation, minus 16t squared. Now our variable here is going to be x because we're not in parametric mode, but that's okay. So it's minus 16x squared, I'm going to move this over, plus 55t x. And then we had minus 26. And I'm going to graph that. I'm going to take a look at my window. I'll graph it and see what happens. Oh, that's not good. I might have a stat plot I have to turn off. Let's see. Let's quit here. I do. I have to turn that stat plot off or it won't graph. Now then, let's try it now. Okay, so there's my parabola. You can see it. I'm going to change my scale here. So I'm going to change this to go from about minus 3 on the x to 3. And I'm going to go from about minus 2 maybe up to 100 on the y-axis. And see what happens. Alright, so there's my parabola. I'm going to change my scale again. I want to get this so I can see it more clearly. So I'm going to start at 0. And I don't need to go to 100, obviously. Let's go to 50. And then graph. Now, this is not the path of the ball. This is just the time traveled. So this time right here where it crosses this x-axis, that is where the ball is at 30 feet on the way up, and this intercept is going to be where it's at 30 feet on the way down, because remember, that graph that we're looking at right there is the solution to this equation. And remember, this equation came about because we set y equal to 30. So what I really want to do then is I want to find the intercept right here, and here's how we do that. We do second function calc, and we're going to tell the calculator to find the 0. It wants left bound, so I'm going to say there, and I have to go to the right. I have to go to, whoa, got a little bit too big, there we go. So I have to go to the right of the intercept that I'm considering. So I do that, hit enter, tell it to guess, and there it is. You can see hopefully there it's 2.87 is what it is. 2.87. So t is equal to 2.87 seconds. That kind of makes sense because when you look up here, when the ball was directly above the fence, it was 2.7 seconds. So another 0.17 seconds passes and the ball then is at 30 feet above the ground, beyond the fence. Well, I don't know if you can tell what we're going to do at this point, but what we want to do is we're going to take this 2.87 seconds and we're going to go back to the x equation up here. So I'm going to bring this original equation down that looked like this. Now I know that the ball was hit when it was struck. It had a 150 feet per second velocity in the x direction. That was from the batter hitting the ball. But what I'm going to do now is I want to slow the ball down so that after 2.87 seconds, it has traveled only 400 feet in the x direction. If I do that, that means that the ball is going to take a trajectory where it's going to hit the top of the wall. Because remember, at 2.87, the ball is going to be 30 feet above the ground. If I can slow its velocity in the x direction, though, it'll be at the top of the wall. So what I do is I come back here and I say, okay, well, I'm going to set this equal to 400. That's the distance out to the wall. But I'm going to calculate a new initial velocity in the x direction, and my time is 2.87 seconds. And I solve for a new velocity in the x direction. This would be the initial velocity that the ball would have to have in the x direction to hit the top of the fence. And that would be 400 feet divided by 2.87 seconds. 400, oops, let's get out of here. Okay, 400 divided by 2.87. and that is right around 13.9. We'll call it 14. Is that right? Oh, I want 400. What are we talking about here? All right, so we want 400 divided by 2.87. There we go. About 139 feet per second. So 139 feet per second. Now, what does that tell us? The ball, when it was struck, the batter gave it an initial velocity of 150. But the ball needs to be leaving the bat at 139 feet per second in order for it to hit the top of the wall. So what's the velocity of the wind? It's going to be the difference between what the batter gave it, 150, and what it really needs to be in order to hit the top of the wall. And that's 11 feet per second. And that would have to be in the left direction. And so that's the answer. It has to be 11 feet per second wind in the opposite direction against the batter in order to slow the ball down in the X direction so that it will hit the top of the wall. Pretty involved problem, but it really helps you see that the motion in the X direction is completely independent of the motion in the Y direction. All right, so I hope you found that helpful. If not helpful, hopefully you found it interesting. And if not interesting, well, I don't know what else I can say. Number 51 was a Ferris wheel problem. I'm not going to go over that one. If you remember how we did the Ferris wheel problem, our y-axis goes right through the middle of the Ferris wheel. Our x-axis is the ground. And if you read that problem carefully, you'll see that the initial position of the rider is right here. And he begins to rotate in that direction. So the same way that we handled this problem last week when we did a Ferris wheel problem, that's how you would work it here. Okay, so I'm going to stop this video, and then we're going to do one more video that's going to cover section 6.4. I don't need you to hand this in. I'm not going to collect this worksheet. But I do need you to hand in your quiz corrections to the substitute if he or she hasn't collected it already. All right, so one more video after this.